Another useful property about light is that it can be polarized. And in order to explain polarization, we first need to look at what light is in a bit more detail. I'm not going to go into this in lots of detail though, because there's a few concepts here that we haven't covered that need a little bit more explanation in themselves. So I'll try and sort of explain it in a way that makes sense. The first thing we need to look at is that light is an electromagnetic wave. That basically means that it's the oscillation of electric and magnetic fields. Now that's the idea that we really could spend a lot more time on. Rather than get bogged down in that though, I'm just going to sort of gloss over it a little and just try and explain what those ideas are without getting stuck into it in lots of detail. So if we look at electric and magnetic fields, that's the reason why light can travel through a vacuum. You don't actually need a medium for electric and magnetic fields to exist. They are there. That's just about the oscillation of a charge that causes then the change in the electric field. The change in an electric field likewise produces a change in magnetic field. So in this case, it's not that we have two separate fields as such, it's that one of them is produced, the electric field change is produced, and then that causes a change in the magnetic field as well. Those ideas are not things that you need to be able to explain in lots of detail though. If we look at the shape of an electromagnetic wave though, we could consider it to be just the change in the electric field over time. So if we look at this representation, imagine that we have the electric field above the axis at these points here, and over here it then goes below. So drawing these lines in here just to sort of show the shape and the direction a little bit more clearly, so that would represent the electric field. Now the magnetic field is going to be on a different axis. So the magnetic field is going to be perpendicular to the electric field, and this diagram here is a little bit tricky to represent on a two-dimensional surface, but I'll do my best. So this plane here, think of the electric field as sort of being in the vertical plane, magnetic field being in sort of a horizontal plane. So the magnetic field actually oscillates in phase with the electric field, but perpendicular to it. So it looks something like that. So these magnetic field lines are now in a horizontal plane coming out this way, and then on the other side going away from. So that's sort of very loosely explained. It's a lot more behind that we could go into, but hopefully that makes enough sense for you. One of the other issues here though is that in that diagram above we have the electric field only oscillating in one plane. So that plane being up and down, or a vertical plane. With light though, it oscillates in all directions. So it doesn't just oscillate vertically, it oscillates horizontally, up and down, left and right, on angles, all sorts of different directions. So light oscillates in all planes. So here I'm going to drop out the magnetic field. I'm not going to bother representing that in this scenario. So if we imagine that we've got that same oscillation that we had before for the electric field, so oscillating up and down, and as the light is travelling in that direction. So I'm only just going to represent the direction that the fields are oscillating here. So again, 3 dimensions trying to be represented in a 2-dimensional diagram. So this would then represent the horizontal plane. We would then have everything in between that's perpendicular to the direction. So we could then represent all of these different planes that the electric field is going to be oscillating through as it is travelling to the right. And again, really messy trying to represent this in a two-dimensional diagram. So hopefully sort of getting the sense there that the electric field is oscillating in lots of different directions. However, now that we've said that light does travel in all of those different directions, when oscillations of the electric field are limited to only one plane, we say that the light has been polarized. So when they're restricted to a single plane, that gives us polarized light. And if we look at the example above, if we were to place a polarizing filter here, so we'll have a look at some polarizing filters in class. Basically, a polarizing filter has a single plane. So just to represent it here, let's imagine that this polarizing filter has a vertical plane. That means that after light has traveled through that plane, the electric field is now only going to be in the vertical plane. So the light has been polarized, there's only light oscillating in the vertical plane now. Now we could turn that polarizing filter sideways so that the axis of polarization is horizontal. That means that the electric field over here would then be oscillating in a horizontal plane. So in this particular case, in that example, it's not just the oscillation of the vertical electric field that is making it through, it's all of the vertical components. So all of those oscillations can have some of their oscillation making it through that filter. So that then means that the intensity decreases by half. Or the intensity of the light is halved in that particular case. If we then were to place, say, a second filter over here that had a horizontal plane of polarization, that then means that over the right hand side here we'd have no light coming out. So we can change that second polarizing filter, we can turn it to different angles to allow more or less light to come through on the right hand side, and that will always come through in the same orientation as this second polarizing filter. So it's a fairly useful idea, that one. It's used in sort of stress testing of materials. You can identify where the stresses are going to be if you allow light to pass through it and have two polarizing filters, so you can see the effect of the polarization as it passes through the material. Some other situations where polarizing filters are used, computers, phones and tablet screens, calculators as well, will often use polarizing filters to allow light to only travel one way through it, or so that it can be controlled in particular ways. You can get polarizing sunglasses, so sunglasses that use polarizing filters, so it decreases the intensity of light by half. The other reason why that's particularly useful in sunglasses is that sunlight that's reflected is actually polarized from the surface that it's reflecting from. So fishermen will quite often use polarizing sunglasses because the light reflecting off the surface of the water is polarized, and so it's more effectively blocked by polarizing sunglasses. The other one that's you might have come across is 3D movie glasses. So they use polarization so that each eye is actually getting a different image because the polarization of the lenses in those glasses are two different orientations, and so you can then project a different image into your right eye compared to your left eye. Your brain then puts them together and interprets the distance as a result. We'll have a look at some polarizing filters in class, as I said, and some of the ways that they can be used.